People very often ask me both how and why I started my podcasting journey. Well, as an engineer, I'm frankly very passionate about math. I wanted to find somewhere to share stories of great mathematicians from Archimedes to Alan Turing and everyone in between. And for that reason, I want to tell you a little bit about my preferred hosting platform, which is Zencaster. Now, before I continue, this is usually the conversation I have with anybody who is wanting to start their own podcast. I know there are so many people out there with passions that they want to share with the world or unique knowledge that they're just looking for a platform to start with. And Zencaster is a wonderful all-in-one platform. What I mean by that is you can do your recording and your editing and use AI to create a transcript and distribute to all platforms, including Apple Podcasts or Spotify or anywhere else where podcasts are played. For anybody like me who might worry at first about what you might sound like on an audio recording, Zencaster's post-production process makes you sound really, really smooth. It automatically removes any of the ums or ahs in your recording. It removes any of the awkward pauses in conversations, and it also helps you to set the right podcast loudness and levels while reducing any background noise, all with the click of a button. It couldn't be easier. Go to zencastr.com/pricing and use my code BREAKINGMATH, and you'll get 30% off your first month in any Zencaster paid plan. I want you to have the same easy experience I do for all my podcasting and content needs. It's time to share your story. Fairly often, I get asked questions about how I got started podcasting with the Breaking Math podcast, and I'll often be asked this question by those who are thinking of starting their own podcast. That is, people who are looking to tell a story or share their unique wisdom with a larger audience or their passions, or maybe just advertise their business or services. I usually like to start this conversation by either showing off or telling about our preferred podcasting platform, Zencaster. Zencaster is essentially an all-in-one podcast hosting platform. On this platform, you can do everything from recording your episodes to editing your audio and video files to distributing your podcast to all podcasting platforms, including Apple Podcasts, Spotify, iHeartRadio, and wherever else podcasts are played. Now, there's more. When I first began podcasting, I used to get very nervous about how I would sound. I would sometimes stutter or have awkward pauses or other audio blemishes in my recordings. Now, Zencaster has a new suite of AI tools in their post-production process that make you sound really smooth. They automatically take out any of the ums or ahs in your recording. Also, they automatically take out any of the awkward pauses in your discussions. The tools will also help you set the right loudness and balance all the levels while reducing any background noise, all with the click of a button. Doesn't sound too bad, does it? You really should check it out. Really, the world needs to hear what you have to say. In fact, I'm going to give you a code below to help give you a large discount. It's all one word, Breaking Math. Go to zencastr.com/pricing and use my code BREAKINGMATH, and you'll get 30% off of your first month in any Zencaster paid plan. I want you to have the same easy experience I do for all my podcasting content needs. It's time to share your...
Before we start the episode, I wanted to say that there is some clicking in the episode. It is some kind of interference. We're still looking into what happened to make sure it doesn't happen again. But it happens probably for about 20 seconds total in the episode at various parts. I cut out as many parts of it as I could, but I could only do so much. So with that in mind, please enjoy episode 39 of Breaking Math. We communicate every day through languages. Not only human languages, but other things that could be classified as language, such as internet protocols, or even the structure of business transactions. The structure of words or sentences, or the metaphorical equivalents in that language, is known as their syntax. There is a way to describe certain syntaxes mathematically through what are known as formal grammars. So, how is a grammar defined mathematically? What model of language is often used in math? And what are the fundamental limits of grammar? All of this and more on this episode of Breaking Math. Episode 39, Syntax Matters. Syntax matters? I'm Sophia, and this is Breaking Math. And with us, we have on Alex Alanis, who works at the Nuclear Weapons Center with Gabriel. Thank you for being on the show.
You're welcome.
So if you want to support us, you can go to patreon.com/breakingmath. For $1, we'll give you a shout out on the podcast with your favorite math concept. So if your name is Jerry and you like tensors, we could say Jerry Tensors. $5 is gold access to Breaking Math episodes early. Sometimes we usually don't get to publish them early, and some outlines. And if you want to donate $22.46 a month, you can get a Tensor poster. Or if you just want to buy that outright, you can go to facebook.com/breakingmathpodcast and buy our Tensor poster there. Our Twitter can be found at twitter.com/breakingmathpod. And of course, we have our website at breakingmathpodcast.com. So, Alex, what is your familiarity with parsing and formal grammars and that sort of thing?
My familiarity with formal grammars is limited. I have a master's degree in mathematics, a doctorate degree in physics. I've done a lot of computer science, so I hear the term parsing, but it's something that the computer scientists are familiar with. In addition to that, I speak 3 Romance languages and in English, of course, so I'm always listening to differences in languages. I don't have a formal background in parsing, per se.
When some of the research, me and you and Gabriel, we've just been talking back and forth about various ideas. And to me, what parsing is it's, there's a formal definition really, but like the best definition I could really think of is like constructing structures out of sequences, like taking a sequence and making a structure out of it. And I remember you were talking about some ideas that you had about artificial intelligence and how it could be used with graphs. Do you want to talk at all about that?
Yeah, correct. In fact, I'm looking at a paper here. It says towards automatically extracting story graphs from natural language stories. And it's work being done at, I see here, Drexel University. And it is a tool which uses natural language processing to extract narratives from Russian kid stories. And it's an attempt to try to understand what stories are being written about, who the characters are, how the dynamics are playing out. At the same time, I have been working on my own time on artificial intelligence and then the application of algebraic topology to read novels and condense avatars from fictional works. At some point, I will meet the problem of natural language processing.
Yeah, and natural language processing is obviously part of all that. That's the first thing we're going to be talking about, really. So buffalo obviously means the animal, the bison, and it means also buffalo in, of course, New York. But a buffalo could also mean to harass somebody. So you could say, for example, buffalo, 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 which means bison from Buffalo, New York, harass. So buffalo, buffalo, meaning buffalo from bison from Buffalo, New York, and then buffalo, they harass.
It's pretty interesting, and that's new to me.
And let's see if you could parse this next one without looking at the answer key. And it has more buffaloes. Buffalo, 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 buffalo. It's basically, you have to sit down with paper and pencil, right?
Yeah, I see that, yeah. I see a tree expanding and a lot of ambiguities forming.
Yeah, that's actually an important point that I forgot to mention. At least the way that Noam Chomsky defines it, and his models have been used for grammar all over the place. Grammar is recursive in definition, so at least natural languages. So you could even go, in that last sentence, it means bison from Buffalo, New York, harass bison from Buffalo, New York, that they themselves harass bison from Buffalo, New York, harass. And then you could say buffalo, 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 etc. And we'll post a meme with this, all these buffaloes on the Facebook page.
So an excellent source for that would be Gödel, Escher, Bach, the book by Hofstadter.
Oh, yeah.
Recursive language.
Yeah, we've talked a little bit about that book. So to continue our thing on natural language processing, we're going to be breaking down the sentence, Mary had a little lamb. So can you identify that you could identify that as a sentence, right?
Yes.
But a sentence has like a few parts, right? Noun, verb, etc.
Correct.
So can you identify, I'll just do the first one. You can start with Mary being the noun,
Mm-hmm.
and then had a little lamb being a verb phrase.
Correct.
The state of having a little lamb. So you could break that down into Mary on one side of the tree, and then the other tree being had a little lamb.
Okay.
So how would you break that down further? Had a little lamb.
Well, there's an object, right? I had a lamb. So there's a verb structure in the middle. Mary had a little lamb. And a little lamb is a little would be descriptive of the lamb.
Yeah, I think the way that I've seen it broken down, usually it's a little lamb is together a noun phrase because
Right.
it's
An object.
an adjective and a noun, and then the determiner a before it makes it still a noun phrase, and then the verb before that makes it a had a little lamb. So that's kind of what we mean by breaking down natural language processing.
So one of the things that's very interesting is I've been playing with Stanford's NLP Core, which is their natural language processing tool.
Mm-hmm.
And you can type in Mary Had a Little Lamb into it, and it will parse it for you in many different and strange ways. And it is the tool for my reading that powers many of the natural language processing tools out there, including Google's engine and Siri, etc. It's fun to type in sentences like Mary had a little lamb and see where how it's parsed.
So how does it parse? I have not played around with this tool. How does it parse ambiguous sentences, like really ambiguous ones?
So first of all, it's an incredibly large tool. It's probably a 100-page manual on it, and there's so many different approaches to parsing in it that I've just begun to explore it. I just do the generic default settings right now, so I can't answer that question other than it has lots of different ways.
Well, cool. And what's the name of that tool one more time?
It's Stanford's NLP Core or Core NLP. I believe it's Core NLP, all as one word. And you can play with it on their website, or you can download it and run it as long as you have, I believe, I think it's Java running on your machine.
All right, so now we're going to talk about what a language is defined mathematically. So first of all, we just have to define a few terms. A symbol is like A, B, or C, or the numeral 1, or whatever. An alphabet is a set of symbols like A through Z, whatever. A string over an alphabet is a finite sequence of symbols from the alphabet. So like words, so like, I don't know, soup or chair. And that would be CHAIR, which would be a sequence of symbols. And then finally, a language is defined as a set of strings, which are the words of the language, or sentences. Let me just give a really simple example of a language. Imagine a language, and the only words in that language are cat and mat. That would still be a valid language, because it has symbols, right?
AMCT.
Yeah, and so we have two words in that language, and the words are cat and mat, so it's not a very interesting language. Another language can be the set of all strings where it's just 3 A's and then 3 B's, or 20 A's and then 20 B's, the same number of A's and B's. That's a language. And that's actually language that's very simple to generate versus something that's a little bit more complicated, like a set of A's and a set of B's and a set of C's where they're all the same length. So do you have any questions about what a language is or how they're used?
Your approach is interesting. One of the most historically important developments of a language similar to what you're talking about is Georg Cantor, who developed set theory in the late 1800s. And he started with wanting to formalize mathematics using pure logic, pure symbols, and grammar. And he said, okay, I'm going to start with the null set. Then I'm going to follow that with the set that contains the null set. That will be my one.
And the null set being, for listeners who don't know, it's a set, or like just a set is like you could think of it like a bucket with things in it. It's like a bucket with nothing in it. So sorry, keep continuing.
So right, so a set that contains the null set would be the one, and it's recursive. The set that contains the null set's 2. And in this way, over several decades, and with several other mathematicians contributing, they were trying to formalize mathematics so that you could present it with a theorem, and after a fixed number of steps. And this is similar to your PC running ones and zeros and ands and or logic, and it freezes on you. It's running binary logic, and you don't know if it's going to take an infinite amount of time to resolve or a finite amount of time. That's essentially the computer science version of the incompleteness theorem. So languages are very interesting in that sense.
Yeah, and there's actually equivalents in just the formal language world to that actually directly utilize the incompleteness theorem. Like there are certain languages that no grammar can generate, no formal grammar, and we'll talk about formal grammar in a sec. All right, first we're going to talk about context-free grammars. And first, we're going to keep doing the terms thing. Okay, first we're going to talk about non-terminal symbols. Those are symbols that are kind of in their own alphabet that are never used in the final sentences produced by the grammar. So they're like intermediary symbols, right? But there's one privileged non-terminal symbol, and that's the start symbol, and usually that's denoted by S. And S is just what you start from. You start with a single letter S. And then there's terminal symbols, which are used in the actual output. So like, those are if we're generating it for language, those are the alphabet of the language. And then there's rules, which is a set of pairs of sequences of terminals and non-terminals, and the other just a sequence of any terminals and non-terminals. But the first one has to have at least one non-terminal. So to break that down, we're gonna do a toy grammar. Let's say that I start you off with the sentence CAT, right?
Okay.
And I give you the rule: A can go to AN. What would CAT become?
Can't.
Yeah, it would become can't. CANT. But if I changed RT to LM, it would become what?
Holcomb.
So that's essentially how these grammars are. That is how they are used to manipulate symbols. So we start with the starting symbol, and the first thing we're going to talk about is a context-free grammar. So context-free grammar, you always go from one symbol to many symbols, and because the reason why is because you don't have the context of any one symbol does not affect its role within the grammar. Does that make sense?
I'd have to think about that.
So like, okay, so before we had the rule A goes to AN, which turns cat to can't, right?
Yes.
And so there we have one symbol going to two symbols. If it were CAAT, it could have become canant, right?
Correct.
So the fact that the A was next to another A didn't matter at all.
Okay.
But if we change the rule to saying like AT becomes to OP, cat would become cop.
Okay.
And the context of A matters in that case because it's next to a T.
I see. Okay, I think I'm following.
Yeah, so in a context-free grammar, we basically expand the symbols. So if you're doing this in a word editing program, you would just take the symbol that you could replace it with, and you could replace it with one symbol, many symbols, or even no symbols. So let me give you an example of a grammar that generates strings of A, B with equal length A and B. So you start with the start symbol S, right?
Correct.
And if S can go to ASB, where A and B are terminal symbols, or S can just disappear, which usually is denoted by an arrow and then epsilon.
Okay.
So what happens if you replace the S in ASB with ASB itself?
If you replace the S with ASB, then you get AASBB.
And if you did that one more time?
It would be AAASBBB, I'm guessing.
Yeah, and then we could replace that with an epsilon with the null string, and then it could just become AAABBB, and that will always generate strings of equal length A and B. So that's a pretty simple grammar. All right, so now we're going to talk about a little bit more of a complicated context-free grammar, and that is the one that defines the normal order of operations, not including exponentiation, so just addition, subtraction, division, multiplication. So we could start with, you start with an expression, right? And an expression could be like 2 plus 3 times parentheses 4 minus 5 in parentheses.
All right.
But an expression can either be a term or a term adding or subtracting from a term. So term plus a term is an expression, or term minus term is an expression. So expression can always be expanded into term plus term or term minus term. Does that make sense?
It does.
And a term can be either transformed into a factor, or a factor multiplying or dividing from another factor. But a factor is either an expression in parentheses or a number. Using that, you could break down any order of operations expression. So for example, let's say, all right, we're just going to do 2 plus 2 as a quick example for this notation. So 2 is a number, right? And plus is, it's used in the grammar. An expression can be term plus a term. So we're probably going to refer back to it later, but right now it's just a symbol. And then we have another 2, which is a number, right?
Yes.
Let's say we want to parse this from the bottom up. A number is also a factor, correct?
I believe so.
So if we replace the numbers here with factors, we have factor and then a plus symbol and then factor, right?
So far, yes.
Now, a factor can also be a term, right?
I believe so, yes.
Now, then we have a term and then a plus symbol and a term. And that can be an expression. And the reason why we brought it all the way back to expression like that is because expression is what we start with. So that is a little bit more of a complex context-free grammar. Just a quick correction here. The grammar I gave is ambiguous. For example, is 1 minus 2 minus 3 minus 4, is that 0 because 1 minus 2 is negative 1, 4 minus 5 is negative 1, 3 minus 4 is negative 1, and 1 minus 2 minus 3 minus 4, is that negative 1 minus negative 1? Or is negative 1 minus 2 minus 3 minus 4, do you do it in a row so you get negative 8? It's not something that is clear from here. So the grammar that would be unambiguous would be expression is equal to expression times factor. Factor equals factor minus term, and term equals parentheses in expression or a number or a variable in some things. But that's not what we talk about in the episode, but here the rest of the episode is. And a computer might use something what's called the shunting yard algorithm to convert it to reverse Polish notation. And I remember you were mentioning earlier that you had a calculator that uses this?
Yes, I love it. It's a Hewlett-Packard 41CX from the early 80s, I believe. It's a reverse Polish machine, and its claim to fame is that it could fly the space shuttle if all the computers would go down.
Well, that's pretty cool. So how would you explain the process of... So let's say you wanted to do 2 plus 2 on a reverse Polish notation calculator. How would you do that?
It would go 2 enter, 2 plus.
Yeah, and the reason why is because you can imagine you have a stack of numbers. So let's say, when you say 2 and press enter, you have a stack, and you could think of this like a block with the number 2 on it. And then you press another 2. And then when you press plus, that's kind of like pressing enter and plus at the same time, because it puts a second 2 on the stack and then takes both of them off with the plus, and it generates a 4. So to parse the grammar or the language that's described by the grammar that we were just talking about, the order of operations, you can use something like the shunting yard algorithm, and it's pretty simple. So let's say you have an output queue or an output series, right? So this is the stuff that will go into the Hewlett-Packard calculator. So let's say we have our 2 plus 2 expression from earlier.
Okay.
So when these are the rules, minus, plus, divided, and times are the operators in order of increasing precedence.
Mm-hmm.
Parens are special operators. And when you put an operator on the operator stack, because there's 2 stacks, there's a stack and there's an output queue, and the stack is a stack is just like a thing where you can put numbers on top of or symbols on top of and take them off. So if I put a 1, 2, and a 3 would be at the top of the stack. If I popped the 3 off, the 2 would be at the top of the stack. If I pushed a 4, the 4 would be at the top. If I popped that 4, the 2 would be back, and so on. So let's say we have 2. Let's actually do 2 plus 2 times 3.
So I would do 3 enter, 2 times, 2 plus.
Yeah, 3 enter 2 times would get 6 into the top of the calculator, and then 3 would have 6 and a 3 at the top of the stack, and then plus would pop both of them off, add them together, and give you 8.
You're right, because I think you said 2. 2
Yeah.
times 2 plus 2 times 3.
Hey everybody, I have a math podcast. But so let's say 2 plus 2 times 3. So we put 2 on the output stack because it's a number. So that's going into the calculator already, is the number 2. And then the next symbol we encounter is a plus. No, that doesn't go into the calculator. That goes on our operator stack. We have another 2, so that goes into the calculator. So you could do 2 enter, which is a different order than you would have put it in, but it's still a valid order. And then
Yes, it is.
yeah.
Because you could do 2 enter 3 times plus.
Yeah, and if you didn't catch exactly why that would work, 2 enter, so we have 2 2s at the top of the stack, and then 3, then we have 2 and a 3 at the top of the stack with another 2 below it. If we press times, the 2 at the top, the 2 and the 3 get multiplied together and re-pushed, so that it's a 6 and a 2. And then when you press plus, it takes a 6 and a 2 and adds them together and produces 8. And that's what's going to be generated by the algorithm. So the rule with the operator stack is that when you're putting another operator on it, it syncs until it basically shoves operators off of it until it is the highest precedence operator. So, for example, times is higher precedence than plus, right? If I put a times on there, it'll be it'll be the first one to get off the stack because it doesn't have to displace the plus. But if they're in the opposite order, it would have displaced the plus. So then at the end of the shunting yard algorithm, we just take all the arguments, all the operators off one by one. So then you get 2, 2, 3 times plus.
Yes.
Or 2, 2, 3, 2. We get a certain number. It works.
Yes.
All right, we talked about context-free grammars. Now we got to talk really quickly about context-sensitive grammars. And we talked earlier about a sequence of like 3 A's, 3 B's, and 3 C's, right?
Yes.
But that cannot be. It is proven that cannot be generated by any context-free grammar at all. Like, no matter how clever it is, it cannot generate that. You need a context-sensitive grammar. And I actually came up with one over the course of doing this episode, and it has 30 rules. And then I find an example on Wikipedia with 10 rules. So if you want a good example of something that generates this language, just go to Wikipedia and search up formal grammars. All right, so as we talked about before, there's some limitations to formal grammars, and one of them being that they cannot reproduce all formal languages. So after this discussion on grammar, do you have any more insight about how that relates to the halting problem or anything like that?
It's interesting, and as I was looking at your toy example here, I'm reminded very much of the rules of biology, of how DNA is turned into proteins with 4 letters, A, T, C, G, and codons 3 at a time. So it's very interesting to see that language has produced what we see on this planet, lots of different species.
Oh yeah, and there's languages within languages there.
Right.
Like, and then there's like hyper compact data, like when there's like when it's offset by 1, but it produces still viable proteins.
Yes.
Which is one of the most insane things in nature. But yeah, and another thing we're going to quickly talk about is Post's correspondence problem. And it's a problem that seems really simple at first, but you'll see why it's maddening. So let's say we have 2 grammars, right? And just to make this easy, let's say that these grammars, let's say that the non-terminals are numbers like 1, 2, 3, 4, 5, 6, 7, 8, 9.
Right.
And the terminals, which are going to be in the final productions, are alphabetical letters. So, for example, you might have like 1 go to AB, 2 go to BC. And so if you did 1, 2, it would go to AB, BC because you expanded 1 and you expand 2. So does that make sense so far?
So far.
So let's say we had two different grammars defined, both from numbers to letters, right?
Okay.
And my question is, given these 2 grammars, these context-free grammars, is there some sequence of non-terminals in both languages that result in the same sequence of terminals? So it seems like this should be an algorithmically easy thing to do on the surface, right?
Seems decidable in a finite number of steps.
But it's undecidable because the Wikipedia page does a very thorough job explaining this. Well, a semi-thorough job. Is that it's possible to set up 2 grammars in this way, such that the answer to this question would answer the halting problem. And are you familiar with the halting problem?
It's the from what I understand, it's the Gödel it's the Gödel problem of, does a theorem stop? Does a computer algorithm stop in a finite number of steps?
Yeah, and it is undecidable. It's undecidable. It's linked really closely to all that, like Gödel and Hilbert and all those people and all their madness. But yeah, basically you could set up in a really clever way. You could set up a computer that would answer a question that is already known to be undecidable.
Right. That's typically the way I understand how the proof works.
And it's really interesting when we run into these limitations, especially in computer science, because it's interesting to think of it as it's easy to think of engineering as something that takes a certain amount of mathematical understanding to master, but it seems like usually it's just you take the mathematical understanding and you find limitations within the physical world with it. Gabriel said you might have had a slight theory about blind spots in physics.
I mean, I've put together probably a 40-page document on limitations of physics, and some of those limitations are inherently built into the mathematics. Like we just decided, I mean, we've just talked about the halting theorem, Gödel's problem of the incompleteness of mathematics. That's one of the problems that all mathematical systems that are rich enough to contain arithmetic are beset with. There are more famous problems than that. If you've ever heard of the Banach-Tarski paradox, which you should look up on the internet, it's very interesting, but it seems to violate logic of volume and density.
Yeah, the basic argument behind the way that this is constructed is creates like a binary path to every point on the sphere, and then it addresses them differently, classifies them into different types of addresses, separates them into different spheres, and builds them into two new spheres.
That's the correct thing. You can disassemble a sphere and reassemble it from its pieces into two equivalent spheres.
Yeah, which is kind of nuts. And of course, like there's undecidable problems in physics, such as if you built a machine that was trying to that posited an undecidable problem.
No, I'm not talking about that. And just to go back to the mathematical case, there's an author out there, Robert Gilmore. Probably he was a mathematician. He was probably not a friend to mathematics in the sense that he had a distaste for pure mathematics, and in his approach, he would think of mathematics as something that should be useful and was inspired by physics. And the gentleman, through his books, goes through all the limitations of mathematics that led through after Gödel through the 1940s and 50s and 60s, and in fact now we don't know what to do. There are 4 or 5 different schools within mathematics on how to deal with these things.
Yeah, it's really interesting. It's almost like we covered a little bit about disagreements in mathematics on our paradoxes episode. I can't really remember the name of it right now, but I remember we talked about these rifts in mathematics happening usually when there's like a big breakthrough that's ready to happen. It seems like that's when mathematicians really disagree, is when they're really going to agree in a kind of new way, but that's maybe me being an optimist always.
What my understanding is, people are practical, and the centricity of mathematical foundations has disappeared in importance, and people are just solving problems.
Yeah, which is not a bad way to go about it. I mean, that's the structure of mathematics until pretty much, the 1600s through the or to the 1900s, with like all the different schools of thought in like India and China and all that.
Right.
But of course now it's a global scale, and they're not localized by geography anymore.
Something interesting on grammar that we haven't talked about yet. So going back to Gödel-Escher-Bach, I mean, the whole book is dedicated to showing that you need full human intelligence in order to do natural language translation, which Google has shown is exactly not true. I mean, they're doing a pretty good job of natural language translation. And it was very interesting how Douglas Hofstadter looked at that problem. In writing his book, I think he had a poem by a French writer, Marot, I believe, that he had it in French, and he would pass it around to many different people who spoke a different first language, and would spin it around the world, and it would come back, and he would see how much it would deviate from the original poem. And there are many interesting examples of that in his book.
Yeah, it is really interesting. He talks also about decidability quite a bit in that book. We actually did an episode on Gödel-Escher-Bach, if you want to go listen to it. I think it's episode 7 or so, GEB. We covered about how he thinks about the proven theorems as like a white tree, the unproven theorems as like a black tree, and the way that they kind of interact and intersect is the land of all the theorems that might be true but cannot be proven within, like, piano arithmetic, which is a formalization of a certain type of integer, and rational arithmetic, right? Is Cantor and all that stuff part of piano? Do you know?
Cantor preceded. He was a set theorist.
Who am I thinking of then?
Piano axioms are. You're correct. Piano axioms are the axioms of arithmetic.
What is the perpetually eidistant or something like that, and the Cauchy sequences. Are Cauchy sequences part of piano formalism?
They derive from it.
Okay, yeah, and Cauchy sequences, just because we're getting into this just for a second, they're kind of like sequences, like they get closer and closer to some irrational number, and they're sequences of technically rational numbers, and that's how you define an irrational number, using rational numbers very cleverly.
So the axioms of mathematics, as set up by Peano, the axioms that are sufficient to encompass arithmetic, are foundational to mathematics, and they're the ones that suffer the Banach-Tarski paradox.
Languages are a way of organizing sequences of symbols, and grammars are a way of describing systems that can be used to generate the sequences of symbols that are from a given language. As we have seen, grammars cannot generate all languages and are a difficult subject of study on their own. But from natural language to calculators, grammars help shape our world. I'm Sophia, and this has been Breaking Math. With this, we add on Alex, and Alex, is there anything you want to plug?
Not at this moment, but thank you for having me on.
Awesome. And I know a few times the term Godel was pronounced Godel, and I know people have complained about that on this episode before, but y'all can die mad about it.
Summer concerts, pool parties, chill nights under the stars. We're stocking up our closet so you're ready to look your best for all of it. At Plato's Closet in West Ashley and North Charleston, we're buying all things summer. So bring in your tees, tote bags, sandals, sunglasses, and more. We pay cash on the spot for gently loved name brand looks. Plato's Closet is the go-to destination for trend-forward teens and young adults who support local and shop sustainable. Visit Plato's Closet today. Plato's Closet, located in West Ashley on Sam Rittenberg Boulevard and North Charleston on Rivers Avenue.